Okay. Hello, everyone. Hello from my side, actually. So now we are going to do some tutorial questions for the model stealing part one, and the model stealing part two, and also robustness concepts are going to be covered next week in the next tutorial. So please keep in mind that next week we also have the tutorial. So the first question you were dealing with was regarding the level of access that we assume the attacker or the adversary has to the model or the system we are having in this case. So usually, based on the attack model, they are divided into three groups of white box, gray box, and black box access. I think it's pretty obvious for everyone that, okay, what's the difference between the two? But I can give you an instance. In the first assignment, you had the white box access to the model, but I think following the papers we provided as a reference, everyone used the gray box signals to basically infer the membership. But you were that was the whole model was available for you. You could go and go on and use the gradients of the model to see how does that behave. So we do not have the mathematical rule that white box methods will going to perform any better, but it's an open question that you can experiment with to see how each of these perform. So if we go in detail from my example, I think it would be pretty clear that in white box model, the adversary has the access to model internals. And these model internals could include the model weights. Even if you have white box access, then you can use the gradients with respect to the weights. And these also could add additional signal to your ensemble of methods you're using. And yeah. And also, if you have noticed, mainly in newer versions of the LLMs coming out, we usually have one series of black box models, and we also have some white box models coming out. But although we have access to the model weights and etc., it's publicly available, but you do not have access to the training data of these models. So there's a distinction between how this is open data or open weight, specifically with the newer trends going on. But possibly it's possible that in white box access model, we also assume that we have access to the training data of these models. So these kind of assumptions are going to vary, and based on these assumptions that we have regarding the attacker and the defender, and they are going to be effective how we design our methods to basically pose our attack against the machine learning models or how we are going to defend it. So if we move one step further and in the gray box method, which mostly the membership inference methods that you saw are working, or you also see in the model stealing, is graybox, and they also assume that you only have the access to the loss value and these, for example, if you are doing a classification task, you have access to the confidence given by this model. And also in the case of the large language models, you have access to these log probabilities that are for the next token prediction. In some kind of gray box access, we can also assume that we know what model family is and also what is the architecture family of this model. Yeah. And we move one step further and we say that, okay, we are becoming more restrictive regarding what we are giving out, and we give the black box method and in black box model. And in this case, you only give out the output label of your model on the task it's performing. Either it's a classification task, you only provide the output label, or it's an LLM, and you only provide the text generated, and you give no further information. For your interest, I would mention that earlier versions of these large language models that were available via APIs, let's say the older versions of the ChatGPT or GPT-4 or the older models, they also provided these log probabilities when you access queries via API, but From certain version on, they remove this access and they only now provide the black box access to these models. So the other question was that, is it restrictive really? Does it prevent the model from being stolen? Well, it is restrictive, yes. You do not have access to extra information. The training data that was used, the model family, the log likelihoods, the model internals, all of those informations are gone. But again, this doesn't stop the adversary from performing its attack. And for example, in the case of model stealing for a classification model, uh, the model does some mistakes, and if an adversary could learn those mistakes and only uses the model behind the API as oracle, it could label those data, and based on those labeled data, it will learn a classifier that actually behaves in the same way, both on the true predictions and false predictions, that actually mimics the behavior of this model. So again, we saw that this black box access doesn't stop the adversary from doing its task, although it is restrictive. Any questions up to this point? I think that's pretty clear. Okay. So before we move on to the next question, it's proper to give the definition of what's the model stealing. So in the model stealing task or a model extraction attack is defined as a case where the adversary steals a copy of this remotely deployed machine learning model, given prediction access to this model. So you might see some different terminologies: model extraction attacks and model stealing attacks. In some literature, they are considered as the same, but I've also seen that model extraction attacks is also used where you want to extract the training data used to train this model. But model extraction attack, if you see my slides and also the question sheet, it means that same as the model stealing attack. So now we move on to the goals. So in the case of the adversary, the goal is not always to just steal this model. So in the reference I provided in the question sheets, they provide a taxonomy for this model stealing. And they mentioned two major goals for the model stealing adversary. The first one is the theft, where the adversary wants to obtain the useful behavior of this model and create a copy of this model for its own. But the other version, maybe it becomes more interesting, and it's called reconnaissance attack. And in the reconnaissance attack, basically you want to learn how this model behaves. And if you could steal this model, you have white box copy of the model on your machine. So you could use it later on to provide more attacks on this model behind the API. For example, I could give you an example where this could happen, where you want to generate adversarial examples, as you will see in the future lectures. And if you know how this model behaves, where this prediction line is drawn, then you could use those behavior of the model to drive more adversarial examples. So in this case, you have white box access and you can do whatever you want to do, although the model is behind the API, and maybe it's also black box access to the model behind the API. Any questions? Yes, please.
Does this stealing includes learning how the model was trained or just what the model is? Like how many epochs, learning rate, or everything that the model was trained on?
That's an interesting question. So it is possible that you use two different learning paradigms, like you use different epochs and different learning rates, but you end up at the same model that behaves almost similarly. In this case, it doesn't matter which approach you have taken to train this target model. What is important that how it behaves on this given input data. So what you want to infer is for example, in a classified task, is how this model behaves, where this classification line is drawn. So major concern regarding this model is that you could draw infer these predictions, how the model behaves, not just the process used to train this model. Okay. So as I mentioned, the stolen model. In the theft model, the stolen model is also the attacker's end goal. But in the other case, the attacker uses this stolen model to pose another adversary against this model. And with that being said, these two types of goals we mentioned ends up with three types of objectives that the attacker could follow in order to steal this model. It's either accuracy or fidelity or functionally equivalent. So in the terms of accuracy, what you care about is to have a model that performs really good. So you don't care if it behaves like this target model or not. You want to have a model which you have trained with significantly lower cost and it performs good. So you don't have to go through the labeling data process. You just use your unlabeled data and use the target model as oracle, and you train your model, and that performs good. You're done. And the other case, you do not just care about if the model performs good, the model you are stealing performs good. You want to mimic the behavior of this model that is behind the API. This means it should match the behavior of this target model in the true cases and also false cases. So you want your stolen model to predict those data points as false if this model behind the API predicts them false as well. And functional equivalent is more general case where you consider your model behind the API as a function, and you want to derive a copy of this model, which is the same function as the model behind the API. So basically what you're caring about is the same function in mathematical terms. This please. That could be considered. Yes. Yes.
Connecting to my last question again, if we have for example, all the hyperparameters in model architecture, wouldn't we have better fidelity or functionally equivalent model? Because the data that we use to steal the model, we might have good fidelity on that, but there might be other data that the model might completely differ on, and we haven't applied that to get our complete model. So by having the same architecture and the learning procedure, wouldn't we get the same, let's say, decision boundary even for the data that we haven't provided when we were stealing the model?
We could possibly, but it depends on which type of model we are considering and which type of learning procedure we are talking about. If we want to consider the function that it has a global minima, then yes, you could go through this learning process and you will end up the same function as the model behind the API. But if you're talking about in terms of the neural networks, which use stochastic gradient descent as its optimization process. So even following the same procedure, you probably will end up with a different function. And the reason is that there are highly level of stochasticity involved in this process. You might use different random initialization with method, and with this different random initialization, you will end up with different function, but it performs the same way. So you should consider this stochasticity. And also in the next question, we'll see that this functionally equivalent is in more specific term NP hard, or if we want to explain it more detail, it's not easily possible to do it. So it depends on which structure you're talking about. So we should clearly define which type of model, which type of learning process we are talking about. It is possible in one case you could do with know what is the learning process and end up in the same function, but in other more interesting cases, maybe it's not possible. Yes.
The difference between fidelity and functionally equivalent, I didn't understand it.
So in the fidelity, what you care about is that you have a function, you have a model, a stolen model, that predicts a given input data point as a true if this target model also predicts that it's true, or if the target model predicts as false, your model wants to predict as false. So you want to mimic the behavior. And as he already mentioned, fidelity could be relaxed version of the functional equivalent. In functional equivalent, you want to have the same function that is performing this task. Yes?
So the difference to accuracy would be that accuracy only works on the true class, so we need the highest prediction for the true class and
Yes.
just care about the negative.
Yes. You want to care about the performance. And if we turn back to the previous slide, in the case of theft and reconnaissance, what do you think about these objectives? So which objective is important for the theft case?
Accuracy?
Definitely. Since the theft case, you want to have a model that performs well, and stealing is your end goal, and that's it. If you have accuracy, if you have a model that performs well in terms of accuracy, then you're done. But for the other case, for the reconnaissance, any ideas? Yeah, please. Functionality. So it could be, if it was possible, but fidelity is more general case that is achievable. And why fidelity is important for us, if you want to later on run another attack against this model, then you want to know how this decision boundary behaves, such that you can design your further attacks on this based on this kind of behavior. So you're not just caring about if your model performs good, you care about if your model mimics the target model as good as possible. So just please.
The stolen model also makes the mistake that the victim model made. So the same mistake as the victim model made. That's in which category this is based on?
Fidelity. So also functional equivalent. So not to just confuse you, what does functional equivalent means here? We will also go on the next slides to discuss this in more detail to see why it's not possible to do it.
I have a question that for fidelity, actually, we are going to make it exactly the same on false and true predictions, but for functionality equivalent, it means that, for example, if the main model is, for example, a linear regression of of 2-3 parameters, maybe we are going to predict and steal exactly the same function in our end, and we are not actually talking about this behavior. If it is false or true, we are going to find out the function.
Yes, exactly. Also, one interesting point is that in the case of linear regression, you have a closed form solution, and if you could find the data, and you could just learn the same function, but in more general cases, it's not possible. So the other question was that why learning this functionally equivalent is generally considered as a hard problem. And the point is that consider a neural network which has n layers, and each layer has d neurons. If you have gone through the NNTI course, you probably have solved this question, where how many equivalent models of these neural networks could have. And you have 2 to the power t times n factorial functionally equivalent networks. This means that if you have activation functions that is an odd function, and you could just switch the layers order, or basically turn off those neurons, and you will end up with the same function, with the same performance, or the same function, but in different format. So we have a class of functions that behave the same way, but we have exponentially many of them. Also, you could go through the reference. They also have mathematical proof for this one, but this was a simple general example why we can generally achieve a functionally equivalent model as our stolen model. So, any questions up to this point?
See how just number possibly neural networks that implies that finding one of them is hard. I mean, if you were to integrate that, of course, it takes mentally much time, but you can still like by training one derive at a functional equivalent from that. I don't know if this is now meant as proof to justify why it requires to get one or.
For the proofs, I would suggest if you go through the paper, and this is just an example that I've provided to show that generally it's not easily feasible to learn such a functional equivalent. For the main proofs, I would suggest go to the paper.
Since there are many ones, shouldn't I think the title here would be not so hard? Because there are many and you can find one.
So let's make it simpler. Based on the query access to a model, can you end up with the same weights the model behind the API? Probably not. That's
You have to give an example, or we can just say there's so many networks or models.
no, there are no details for proofs or something, whatever content here is. So the other questions regarding the sharpening the mix match algorithm. So mix match basically is a semi-supervised method that could also be used to extract the model. And this mix match algorithm had two important parts. And the first one was the sharpening, and the other one was the mix-up. So here the goal was to know what is the effect of different temperatures used in the sharpening on the output distributions, and also what is the reason we are using the sharpening. So you had four options, whether t equals 1 or less than 1, approaches 0, or it's greater than 0. I think it was greater than 1, but yeah, I had a mistake in the slide. So in the first case, if you have t equals 1, then you end up with the same probability distribution. And for the smaller than t is smaller than 1, then you basically get your large probabilities larger and the smaller ones get smaller. You could also have one numerical example with simple ones, and you could calculate to see the effect. But the overall goal is to see how this performs when you end up with different temperatures. And with t approaching to 0, your distribution becomes one hot. It means the true class becomes the most significant and the other lower ones approach to 0. And with t greater than 1, the distribution becomes more uniform. So based on this and also the goal that mixed match algorithm has, which one do you think is the proper option to use? And based on the considering the fact that why we are using the sharpening phase in the and basically the second and third one could be considered almost the same, but yes, and the correct answer would be to t going through this towards 0, and actually it's a hyperparameter, it should be tuned, but smaller values is preferred since you want to learn a low entropy distribution of this labeling process. So if you use the lower values for t, then it means that model becomes more confident based on the predictions made, and it encourages the model to learn a clearer class boundaries. And the next part of this mixed match algorithm was the mix-up. And the question was that what is the reason for using this mix-up? And for the reason we could mention is that, again, it encourages the model to basically learn a smoother decision boundaries. And note that we are using the same model to label the unlabeled data. So we have some kind of uncertainty involved in here. So with using the mix-up, we also encourage the model to have smoother decision boundaries and improve the generalization at the end. Any questions up to this point?
This is only label. Pizza, because we have already labeled for labeled plate.
I think mix-up uses both of them. Both of them. Mhm.
Because we do not have a label for unlabeled forms. Shouldn't be fair on them?
We predict the labels for unlabeled samples.
And you using the mix-up, you are shifting those that predicted towards the actual data that are labeled. So basically, you are smoothing the decision boundaries here. So, and the last question was involving the estimation of the privacy leakage. And estimation of privacy leakage is important since in the case that you want to have a defense against attack. And for example, in one of the examples that you saw in the lecture, whether you want to adjust the cost based on this leakage, and having an estimation on what is this leakage is important. And one of the ways that we could use to basically infer this leakage was the margin leakage. And it is measured as the 1 minus the probability predicted for the maximum, maximum probability predicted minus the second maximum. And this gap between these two probabilities basically shows how model confident is that given this data. And having this notion of confidence, it could give us a sense of where this decision boundary is drawn. So basically, it's a simple mathematically to compute, but it's also important to consider why this is considered as a privacy leakage. And for margin leakage, in order to calculate it, is 1 minus these two terms. And this case is 0.4 and 0.3.
This represents that it's not good because the decay is really high, right?
And the value, yes.
Just because the second highest and the highest class, the difference is not a lot, so there's a lot of leakage into it.
And the other is the entropy leakage. So this also basically involves calculating the entropy given these predicted probabilities, given different classes, and entropy represents the amount of information is stored in this given input data. And well, the calculation wise is again simple. You will just to calculate the sum over p log p, but notation wise, why we use this kind of basically information theoretic measure to basically calculate the amount of privacy leakage is that the higher this entropy, basically the more information you have regarding this given vector or probabilities predicted given this data. So it's some kind of information theoretic view, and you could use the same notations here as well. And the other privacy leakage, actually based on the given number of votes for private KNN, this is also the suggested way how we could utilize this error function to basically calculate the amount of information leakage, privacy leakage, based on the difference between the noisy aggregated label minus the other ones. And note that this is one single case I've calculated here. If you have the number of votes for all of these prediction labels, and you have to sum over all of them. So it's just a simple example to just give you an intuition how this is calculated. Any questions? I will share these slides later on so you can access.
Could you explain the equation behind that thing? This is like, it's very.
The error function as
Yeah.
privacy leakage. So it could be also considered the same as the first one. In this case, you have the noisily aggregated labels, and instead of the probability distribution over the classes. So in this case, we use the error function to basically calculate the amount of the privacy leakage. Also, if Adam has any more explanation.
Yeah,
in this regard.
we could also error function on the groups. But think
Mhm.
about this predictably that if n sub I star minus n sub I is of like high distance, meaning that the model this model ensemble was considered about the I star class. Actually, this is prediction actually that was confident, so we don't have like this case sample concentration boundary. However, if you have features that voted similarly on class and class I star and class other class I, then they were not sure which really class is correct. So then actually from the sample landed on the string boundary, you have this basically lack of the majority voting for the features. Actually, the sample actually reveal more information about this.
Makes sense.
So this privacy leakage is derived directly from the Pattern method. Actually, this Pattern method actually uses exactly this function to compute the privacy leakage for epsilon. It's almost exactly that. There are some so Pattern has also additional here constants. But this is also how Pattern computes the epsilon value during the computation, during the answering the question to the journal.
An error function is an arbitrary function?
No, it's just an error function. So it's basically standard function that is used in privacy.
Yeah.
And also beyond privacy, it's just standard. It's nothing special. It's just very standard function.
Just a question. So larger the difference between the highest and the second highest class, larger the leakage reason or smaller the leakage, considering the distance between the two classes?
So basically, the larger the difference between the mode counts, the smaller the leakage. Because so if you think about Patel, so changing one feature wouldn't change the prediction of the ensemble. So you have high difference between the top class and the second class. But if the predictions are say the same, so you don't have to even max class. You have basically just two classes have the same number of vote counts. You change one feature, that this will influence which class is selected as the return class. The leakage is much higher if you have almost same vote counts in Pattern. The same applies here.
So we raise it a lot or less? I mean, the difference is less of 10. Here, do we consider them to be similar in a way or different?
So in practice, a difference of more than 2 is enough. However, in this computation, we take into account really this distance. So the higher the distance, like, for example, like 170 for top class and 10 for the second class, then you almost not have a solution. So the higher the distance between the max count and the second count, the less there was.
Any more questions? Okay, thank you very much.